Hi, welcome back to my channel. My name is Gina. In this video, we're going to find an exact value of a sine area. I have a video on how to estimate an area between a curve and the x-axis. If you haven't watched that video, I'll put the link up there and watch that video before you continue this one, because this video will be based on the concept from that video. So from that video, we estimate the area between a function 2x minus x squared over the interval 0 to 2. And in this video, we're going to find the exact sine area of the same curve over the same interval. Our estimation from the last video, it was 1.25. Let's see how close our estimation is to the true value of the sine area. So similarly, the first step, we're going to divide the interval into subintervals. The interval is from 0 to 2. And we're going to split this into many subintervals. Suppose here we have n subintervals, and the delta x, the width of each subinterval, is 2 minus 0 over n, which is 2 over n. And if we look at the right side point of each subinterval, x1 would be 0 plus the interval delta x. And similarly, x2 would be 0 plus 2 delta x, because x2 is 2 delta x away from the starting point 0. And x3 would be 0 plus 3 delta x. A general form to that would be xk, which equals to 0 plus k delta x. So the second step, we're going to substitute the delta x into xk. So we found that xk is k times delta x, and from the first step, delta x is 2 over n. So xk is 2 over n times k. Now the third step, we're going to substitute this xk into our function. So we're going to find the y value at xk, which equals to 2 times 2k minus xk squared. And xk is 2 over n times k. So f of xk is 2 times 2 over n times k minus 2 over n times k squared, which equals to 4 over n times k minus 4 over n squared times k squared. Then the last step, same as before, we're going to sum up the area of all the rectangles. I'll denote the sine area as SA and the interval from 0 to 2. If we were going to estimate this, from the previous video, we know that it equals to the sum of base times height of each rectangle. Using the terms we have here, it equals to sum of delta x times the height, which is f of xk. And the index starts from 1 to n. However, if we want to find the exact value, we need to take the limit as n approaches infinity. So we have infinitely many subintervals. So the exact value of sine area over the interval 0 to 2 equals limit as n approaches infinity of sum of delta x times f of xk the index starts from 1 to n. Now we substitute the delta x and f of xk into this equation. So this equals to limit as n approaches infinity of sum of delta x, which is 2 over n, times f of xk, which is 4 over n times k, minus 4 over n squared times k squared. And the index starts from 1 to n. Now we expand the equation. Limit as n approaches infinity of sum of 8 over n squared times k minus 8 over n cubed times k squared. The index starts from 1 to n. Now we can use the summation rules to pull out the constant and also expand the first and the second term. So this equals to limit as n approaches infinity of 8 over n squared times sum of k starting from 1 to n minus 8 over n cubed times sum of k squared starting from 1 to n. Then we can use the summation formulas to substitute sum of k and sum of k squared. So this equals to limit as n approaches infinity of 8 over n squared, and sum of k is n times n plus 1 over 2 minus 8 over n cubed, and sum of k squared is n plus 1 times 2n plus 1 over 6. Now let's simplify the equation. So this equals to limit as n approaches infinity of 4 times n plus 1 over n minus 4 over 3 times n plus 1 over n times 2n plus 1 over n, which also equals to limit as n approaches infinity of 4 times 1 plus 1 over n minus 4 over 3 times 1 plus 1 over n times 2 plus 1 over n. Now if we take the limit as n approaches infinity, 1 over n will go to 0. So after we use the chain rule, we'll get 4 times 1 plus 0 minus 4 over 3 times 1 plus 0 times 2 plus 0, which equals to 4 minus 8 over 3, which is roughly 1.33, which is pretty close to our estimation, 1.25. That is the end of the video. I have a course on Udemy on this section of Calculus 2. It's free to enroll. I'll put the link down below. You'll also get an assignment with solutions at the end of the course for you to do some hands-on practice. If you like my videos, please subscribe to my channel and give me a thumb up. And I'll see you in the next video.